Paul Joseph Steinhardt is an American theoretical physicist and cosmologist who is currently the Albert Einstein Professor in Science at Princeton University. In addition, Steinhardt co-founded and is the current director of the Princeton Center for Theoretical Science academic work. Steinhardt's research has spanned problems in particle physics, astrophysics, cosmology, condensed matter physics, geoscience and photonics. In cosmology, some of his important contributions include: he is one of the architects of inflationary cosmology, which has become an essential part of the Big Bang theory. He also presented the first example of eternal inflation, which ultimately revealed the multiverse and caused him to doubt the inflation theory he had pioneered. He then became one of the developers of the leading competing alternatives to the Big Bang, the ekpyrotic and the cyclic theory of the universe. Steinhardt co-authored the first paper to compute the complete imprint of gravitational waves on the spectrum of temperature variations and on the B-mode polarization of the cosmic microwave background. He also co-authored the first paper to show that, based on observations at the time, most of the energy in the universe must be dark energy, enough to cause the universe to expand at an accelerating rate today. Several years later, the conclusion was confirmed by supernova observations. Working with various collaborators, he introduced the concept of quintessential dark energy to further explain the accelerating expansion of the universe. Steinhardt also co-authored the concept of strongly self-interacting dark matter to explain the missing mass of the universe, and to address anomalies previous theories of dark matter were unable to explain. In condensed matter physics and geophysics, Steinhardt and his then-student invented the theoretical concept of quasi-crystals, and even introduced the term quasi-crystal to the lexicon. The two were also the first to correctly identify a puzzling aluminum-manganese alloy with icosahedral symmetry, announced by Dan Shechtman and collaborators in 1984 as the first example of a quasi-crystal to be made in a laboratory. The following decade, Steinhardt launched a worldwide search for a quasi-crystal formed by a natural geophysical or astrophysical process. His team eventually discovered a candidate in a Florentine museum collection. Their discovery was recognized by the International Mineralogical Association as the first natural quasi-crystal, and they accepted the team's proposed name for it, icosahedrite. Over the next year, disparate clues were pieced together about its origin, finally pointing to a remote mountain range in Chukotka, on Russia's Kamchatka Peninsula. 2 years later, Steinhardt initiated his first-ever field expedition, and led a team of geologists to the region. As a result of that expedition, and nearly 3 decades after first inventing the concept of this entirely new form of matter, Steinhardt managed to discover the first quasi-crystal formed through a natural process, which his team later proved was part of a 4.5 billion-year-old meteorite. They also discovered a second quasi-crystal named decagonite, along with a new crystalline mineral that was named Steinhardtite, in his honor. In photonics, Steinhardt has been an innovator in using quasi-crystals and other novel patterns to design photonic materials, including a new class of material called hyperuniform disordered solids. More recently, Steinhardt helped design and fabricate a photonic quasi-crystal for efficiently trapping and manipulating light in selected wave bands, and is one of the leaders developing isotropic photonic materials known as hyperuniform disordered solids. Steinhardt and his Princeton colleagues later helped form a company named Etaphase, Inc., to develop commercial applications for those materials. In a ceremony at Perimeter Institute in 2015, Neil Turok said of Steinhardt, "I know of no other scientist, no other theoretical physicist alive who has a clearer focus on whether our theories and ideas are relevant to the real world. And that's always what he's after." Inflationary cosmology. Development of theory beginning in the early 1980s. Steinhardt co-authored seminal papers that helped to lay the foundations of inflationary cosmology. In 1982, Steinhardt and Andreas Albrecht constructed the first inflationary models to produce sufficient accelerated expansion to smooth and flatten the universe and then gracefully exit. The inflation is caused by the energy stored in a scalar field that permeates space and varies with time from high energy to low energy. This work is especially significant, because it has been the prototype for most subsequent inflationary models. The Albrecht-Steinhardt paper is also notable because it introduced the concept of Hubble friction in 1982, a gravitational effect that plays the key role in the slow roll of the inflaton field, enabling the generation of density fluctuations. Hubble friction and slow roll is an essential element in most subsequent inflationary models. James Bardeen, Steinhardt and Michael S. Turner then produced the first computation showing that density fluctuations can be generated from quantum fluctuations during inflation using a relativistically gauged method of calculation in 1983. They showed that it is possible to produce a nearly scale-invariant spectrum of fluctuations with a small tilt. Properties later shown by observations of the cosmic microwave background to be features of our universe. Contemporaneous calculations by several other groups obtained similar conclusions using less rigorous methods. Later that year, Steinhardt presented the first example of eternal inflation, which would eventually be shown to be a generic feature of inflationary models that leads to a multiverse of outcomes instead of the single smooth and flat universe, as originally hoped when first proposed. This was significant research, because Steinhardt would eventually argue that if every outcome is allowed, inflation makes no predictions. Consequently, eternal inflation may be the Achilles heel of the inflationary picture. Dale Lahr and Steinhardt teamed up in 1989, and introduced extended inflation based on scalar tensor theories of gravity that introduced a new way to solve the graceful exit problem through bubble nucleation and collisions rather than slow roll. Robert Crittenden, Rick Davis, J.R. Bond, F. Stathiou and Steinhardt performed the first calculations of the complete imprint of gravitational waves on the cosmic microwave background, temperature and E-mode and B-mode polarization power spectra in 1993. Steinhardt's major contributions to the inflationary theory were recognized in 2002, when he shared the Dirac Prize with Alan Guth of MIT, and Andre Lind of Stanford. Criticism around the same time. Steinhardt publicly broke ranks with Guth and Lind when he began to voice his profound concern about the multiverse producing an infinite variety of patches of space spanning every conceivable cosmological outcome, including an infinite number of patches that are not flat, not uniform, and without nearly scale-invariant perturbations. Steinhardt's warnings were unexpected, because he had played an important role in developing inflation and revealing the multiverse when he introduced the first example of eternal inflation in 1983. He has emphasized that due to the multiverse, the inflationary model is so flexible that no observation or combination of observations can disprove it. Also, none of the observations that have been made since the theory was first introduced in 1981 can be interpreted as actually supporting the theory, because any other result would fit the theory just as well. This is significant, because the ability to disprove a theory through experiment has always been considered the key to distinguishing science from non-science. In a widely discussed pair of papers published in 2013 and 2014, Anna Ajace, Abraham Loeb and Steinhardt showed that observations from the Planck satellite reported in 2013 disfavor the simplest textbook inflationary models. These papers showed that the remaining models require more parameters, more fine-tuning of those parameters, and more unlikely initial conditions than the simplest models. This predicament for inflationary cosmology is often referred to as the unlikeliness problem. These conclusions were reaffirmed and strengthened by measurements subsequently reported by the Planck satellite team in 2015. Cyclic, ekpyrotic theory of the universe. Early development. Steinhardt has been a leading developer of cyclic and ekpyrotic cosmology, working with Justin Cowrie, Bert A. Ovut and Neil Turok. Steinhardt introduced the ekpyrotic theory, which imagines a big bounce instead of a big bang. According to this model, the current expanding universe emerges from a bounce that occurred 13.7 billion years ago, and that is a result of the preceding universe. The smoothing and flattening of the universe and the generation of density variations occur during the phase of slow contraction before the bounce, and remain after the bounce. In the original example, the bounce corresponded to a collision and recoil of brownness along an extra dimension in string theory. But more recent versions do not require extra dimensions or string theory. Instead, quantum fields with potential energy evolving in space-time, similar to inflationary models, can be used. Steinhardt and Turok then incorporated the ekpyrotic idea into a bolder proposal, the cyclic theory of the universe. According to this model, the bounce represents the end of a cycle of evolution, the transition between a preceding period of contraction and the next period of expansion. This cycle repeats at regular intervals every trillion years or so. Dark energy is predicted by the model and plays an essential role stabilizing the cycles. Steinhardt and Turok proved that the cyclic process can repeat itself not just indefinitely, but also infinitely into the past and the future. Notable features. Earlier cyclic-type cosmological models had an entropy problem that the new cyclic model evades. According to the second law of thermodynamics, entropy always increases. The entropy produced in one cycle adds to the entropy produced in earlier cycles. If the universe contracts and the entropy produced in previous cycles lies within the observable universe at the beginning of the next cycle, the added entropy will cause the next cycle to be longer than the one before, or, projecting backwards in time, earlier cycles would have to be shorter and shorter, eventually reducing to zero duration. This reintroduces the problem that time must have a beginning. In the new cyclic model, the observable universe just after a bounce only occupies a tiny fraction of the space occupied by the observable universe a cycle earlier, and so only contains a negligible fraction of the total entropy. The entropy building up over the cycles is almost entirely beyond what can be seen and cannot influence the next cycle. Cyclic models have two big advantages over inflationary models. First, they do not produce a multiverse because the smoothing and flattening occur during contraction rather than inflation. This means that, unlike inflation, cyclic models make definite predictions and are falsifiable. Second, cyclic models explain why there must be dark energy. The accelerated expansion caused by dark energy starts the smoothing process, and the decay of dark energy starts the contraction. Predictions. Because cyclic, ekpyrotic models do not produce a multiverse, they make definite predictions which, if shown to be wrong, disprove the theory. One prediction is that, unlike inflation, no detectable gravitational waves are generated during the smoothing and flattening process. A second prediction is that the current acceleration expansion must eventually stop and the vacuum must be eventually decay in order to initiate the next cycle that cause the contraction. The cyclic model may naturally explain why the cosmological constant is exponentially small and positive, compared to the enormous value expected by quantum gravity theories. The cosmological constant might begin large, as expected, but then slowly decay over the course of many cycles to the tiny value observed today. The discovery of the Higgs field at the Large Hadron Collider may provide added support for the cyclic model. Evidence from the LHC suggests that the current vacuum may decay in the future, according to calculations made by Steinhardt, Turok and Zach Bars. The decay of the current vacuum is required by the cyclic model in order to end the current phase of expansion, contract. bounce and a new era of expansion. The Higgs provides a possible mechanism of decay that can be tested. The Higgs field is a viable candidate for the field that drives the cycles of expansion and contraction, dark energy and dark matter. Steinhardt has made significant contributions researching the dark side of the universe, dark energy, the cosmological constant problem and dark matter. In 1995, Steinhardt and Jeremiah Ostriker used the concordance of cosmological observations to show there must be a non-zero dark energy component today, more than 65% of the total energy density, sufficient to cause the expansion of the universe to accelerate. This was verified 3 years later by supernova observations in 1998. It was first posited by Steinhardt's team as an alternative to the cosmological constant, which is constant and static. Quintessence is dynamic. Its energy density and pressure evolve over time. The introduction of quintessence underscored the importance of measuring the equation of state of dark energy in order to determine the cause of the acceleration of the known universe. Steinhardt has also proposed various approaches for solving the cosmological constant problem using quintessence, including tracker and k-essence. These forms of dark energy would have the property that they cannot dominate the expansion of the universe and initiate cosmic acceleration until later in the history of the universe, after galaxies form. In accord with astronomical observations, the cosmological constant problem can be naturally resolved in the cyclic model, according to Steinhardt and Turok. In 2000, David Spergel and Steinhardt first introduced the concept of strongly self-interacting dark matter to explain various anomalies in standard cold, dark models. Most prior models of dark matter assumed it is composed of weakly interacting massive particles that clump together through gravitational attraction, only because the other forces between particles are too weak to affect their motion. The SIDM picture proposes that the other forces are strong enough for the particles to scatter off one another in regions where they would otherwise pile up in the center of galaxies. Also, the scattering would reduce the mass of dwarf galaxies in orbit around larger galaxies because the dark matter particles surrounding the larger galaxy would scatter and, thereby, strip off the dark matter surrounding the dwarf galaxy. This idea is particularly interesting because there is astronomical evidence suggesting that galaxy cores are not cuspi, and the most massive galaxies predicted by simulations based on WIMPs are not observed. If the SIDM picture is correct, searchers for WIMP dark matter will find nothing, and different approaches will be needed to determine the identity of dark matter. Steinhardt, Spergel and Jason Pollock have proposed that a small fraction of dark matter could have ultra-strong self-interactions, which would cause the particles to coalesce rapidly and collapse into seeds for early supermassive black holes. Amorphous solids. Steinhardt's research in condensed matter has centered on the properties of non-periodic solids, glasses, amorphous semiconductors, metals and quasi-crystals. He constructed the first computer-generated continuous random network model of glass and amorphous silicon in 1973, while still an undergraduate at Caltech. CRNs remain the leading model of amorphous silicon and other semiconductors today, working with Richard Albin and D. Ware, he used the computer model to predict structural and electronic properties. Working with David Nelson and Marco Ronchetti, Steinhardt formulated mathematical expressions, known as orientational order parameters, for computing the degree of alignment of interatomic bonds in liquids and solids in 1981, applying them to computer simulations of monatomic supercooled liquids. They showed that the atoms form arrangements with finite-range icosahedral bond orientational order as liquids cool. The order parameter continues to be used in diverse areas of chemistry and material sciences. The discovery of icosahedral orientational order stimulated the discovery of quintessence.